So it's Monday afternoon, and I am going to do, for environmental plant physiology, I'm going to go through last year's midterm exam mostly to inspire you, to help you see the answers and inspire you to practice the questions. The last year's exam is pretty challenging, but that's the nature of take-home exams. For sure I'll ask different questions, but similar. So as a broad overview, it's good to be able to work the questions on this exam, but since the new questions will be different, it's better to have a conceptual understanding. So let's start with the title of the book. If you notice on this, it's a good place to start studying because this whole page is full of equations, and you'll notice that we have now covered all of the equations on this except one, and the one left is a real simple equation. Here's our energy balance equation, and you can see from the exam that leads to all kinds of questions. Here's the Stefan Boltzmann equation feeding into net radiation. Even this alone, net radiation has some components, just to get that. Here's gas transport flux, which is either transpiration or photosynthesis, equals G, which is to model conductance, times the driving gradient. In this case, CI. So this flux here would be photosynthesis. If this was HI and HA, then it would be transpiration. Let me make a point about that since it's come up. These things are just as valuable as work in the test because they're concepts. If we're doing water use efficiency, WUE, of course we've got delta CO2 and delta H2O, and delta CO2 is Ca minus Ci, that gradient, and delta H2O is Hi minus, in this case we put HA first, HA minus HI. These, and then of course, as you remember from the last lecture, this is times 0.625 because of the slowness of diffusion. Now here's the point. I want to put this in a different color. These are the absolute values of each of these. Shu Yang pointed that out because the gradient goes in for one and goes out for the other. So there's water use efficiency. Just to review that. Let's go down. Here's the bottom half of the book. We haven't gotten to plant water potential yet, but these pitchfork symbols are plant water potential. So don't worry about that for now, we haven't got there. Here's the relative growth rate equation, which everybody is now using to look at the exponential growth of coronavirus. And then this one, light penetration into a canopy, Beer's law. So you can see the only part we haven't done yet is plant water potential, and there's all the equations. So if this was a class and there's people, I would ask for questions, but let's take, here's the exam with last year's answers written in. This class has done really well on this type of a question. We've reviewed it and everybody studied it. A few years ago, people missed this a lot, so I put it on the take-home again to review it. And we can review this just quickly right now, but I think these are a little bit harder questions because it's take-home, but let's take a look at this. First of all, the leaf is below air temperature in the day. That only happens with well-watered leaves, low humidity, but it happens. And then it's of course below humidity at night. If, the first question, the albedo decreases And albedo, remember, is reflectance of short wave, so if that decreases, the leaf is going to absorb more short wave radiation. But now look at this. This isn't exactly, the column for leaf temperature is not on this question anymore. But if the albedo decreases, long wave absorbed, albedo doesn't affect long wave. So the first answer right here is NC. Emitted radiation, that's not affected by albedo directly, but let's take some, but the leaf is going to warm up because the albedo went down. So shortwave radiation absorbed is going to go up. And if the shortwave radiation absorbed goes up, the emitted is going to go up because the leaf is warming up. If the leaf warms up, nothing else changes. What happens to transpiration? Goes up because it's a bigger vapor pressure deficit. Now, if the leaf is below air temperature and it warms up, it gets closer to 0 delta T, and if it gets closer to 0 delta T, this one goes down. This is the delta T, the absolute delta T for that. I'm not sure if I need to go through the rest of these because these are so similar to previous things. I can tell you that if just think through what happens to leaf temperature. Let's just talk about that. And once you know that, you can figure out anything else. If it's a clear night and the wind decreases, the wind is what's warming the leaf up. If the wind decreases, the leaf is going to cool off and it's going to be cooler. So the second one here is leaf cooler. We run sprinklers for frost protection. That's going to warm up the leaf because it was below temperature, now it warms up. And from the cooler and warmer, you can drive the rest of these. So let's go now to the second page. These are just true false. They're a little bit tricky. I can give you a hint. All of these are false. There's like little typos. All of these are false, and you have to look for the exact details. So if you can't see why they're false, send me an email. This one is the sky radiation. Now note, here's the sky, and here's the ground, and if this is clouds, the energy going down and the energy coming up are equal, and so this is close to 0, and on this, here's 0. So these numbers up here are cloudy periods, and then when the sky is very clear, it's a really negative number. So negative numbers are clear sky, numbers close to 0 are cloudy sky. I think that says indicate where there's clouds. All right. This is just a graph of turf temperature or ground temperature and air temperature, and it says when's the highest, when's the lowest. Here's a really high period right here. When there's a huge driving gradient, and then look at over here, somewhere in here is the lowest, right there, when the ground is colder than the air. Now, note that this is also a classic radiation frost because the air temperature never got below freezing the whole night, but oh my goodness, the plant got well below freezing and it was there for 6 hours. So it's a clear night with a classic radiation frost. And this just asks you for the most positive and negative values. Take this. It doesn't look like I filled in this second one, but the second one is -5, see, most negative temperature difference, and it occurred at about 11 p.m., sorry. I'm not sure I gave you that on the graph. So there's the two answers for this, interpreting this graph. Number 5, how would we use plant growth analysis to see if differences are caused by radiation capture or increased photosynthetic efficiency? Now this is something we do all the time in this lab. But remember, crop growth rate, NAR times leaf area index, or on a single plant, remember RGR equals NAR times leaf area ratio. So if we measure the leaf area and the growth, we can separately partition out photosynthesis from radiation capture. These parameters are how well the plant spreads out its leaf and captures radiation. So if this goes up, it was caused by better radiation capture. If this goes up, it's caused by better photosynthesis. Sometimes it could be a little of both, but depending on the species, increased radiation capture is the biggest thing. So this just says describe how you would use this to partition this out. It's not a calculation answer. That's number 5. Number 6 is going to be, I'm not going to be able to work that out right here, but this is a classic energy balance equation, and after all this it says what's the leaf temperature need to be to balance the equation. So you work through the component parts of this to get this. And let me, here we go, put this over here. Step 1, and this is the key to solving any of these, is look at the component parts. And let me erase this. This is pretty simple. Step 1, here's the leaf. This is an agave with vertical leaves, but we'll still do this. So we've got shortwave in, we've got shortwave reflected, we've got reflected radiation for shortwave. We've got transmitted radiation for shortwave. Phi shortwave, after these are added, all added up, comes out to be, this is phi shortwave absorbed, comes out to be 850 watts per meter squared. Now you got to put the numbers in here, but this is what it comes out to for shortwave. Now, and here I can do this in a different color. We got to do long wave from this, and we do the same thing for long wave. And maybe I'll do red. That's a good color for long wave. We have long wave in, long wave in. Absorbed long wave, phi long wave, absorbed, comes out to be 690. Now note, this isn't, we don't have emitted long wave yet because we don't know that. We just know the incoming long wave. And these are, you look these up or calculated. So now we have the two numbers together, and 1540 watts per meter squared for total energy absorbed by that leaf. Now we go to radiation absorbed equals transpiration plus conduction and convection. So far so good. We know conduction and convection. We know this one is 1540. We know this is 400 because that was the missing component in here. 400, but that's now given in the question. So hold on a second. We know transpiration in this. This is one step. Phi emitted equals absorbed plus T plus C squared. What we're after is phi emitted here. We know the absorbed, we know this. Transpiration is given, but the units are, let me read it up here. Transpiration, 0.1 millimoles per meter squared per second. Put that up here. 0.1 millimoles per meter squared of leaf per second. It's all per meter squared. Now we need to multiply that by the latent heat evaporation, 2.45 megajoules per liter, to get it into watts, to put it in here. And a joule per second is a watt. And you multiply this together, and this comes out to be 4.4 watts. This is a tiny transpiration rate. This agave plant is really minimal transpiration. So we do this math, and these are cooling, absorbed, so this plus is minus 4.4, and this is plus a negative number. So we take 1540, subtract these, and phi emitted comes out to be 1135.6 watts per meter squared. Now we're most of the way there. Phi emitted watts per meter squared. Now we just need to say what would the leaf temperature have to be to get there. There's two ways to calculate leaf temperature. First of all, the emissivity of this leaf is 0.95. I'm going to put emissivity right here. That means the leaf has to get a little bit hotter to emit this radiation. So when we do this, we get 1195 watts per meter squared. And now remember, the leaf has two sides. It can go up, it can go down. So we divide that by 2, and we get equals 598 watts per meter squared. Now, you can do this in two ways. Look it up in the table. What temperature would it take to give you this emission? Or, excuse me, or you can solve for energy equals sigma, emissivity times sigma times T to the 4th Kelvin. And when we rearrange this, we get energy meter squared, over E times sigma. This is T, and when we take the fourth power off of here, it goes over there. So we get the fourth root of this. So you can rearrange this to solve for temperature. That's temperature in Kelvin. If we look this up in the table, 598, let's see where we're at, 596, it's 47 point something in this table. And in fact, the answer to the question is 47.2 degrees C. So this is the step-by-step how to work chamber, or question number 6. With not every single step in here, but at least the intermediate numbers and how to set the question up. Question 7. This question asks us, since some of the energy goes into photosynthesis, how much does that cool off the leaf? It's energy it doesn't have to get rid of because it's going into photosynthesis. So the first part of this, and now I'm going to erase this. Give ourselves some more room to work stuff here. We'll leave that up there, didn't take too much room. The first step to working this is, first of all, we've got conduction and convection. This is all going to come down to conduction and convection, is 2 sides of the leaf times K times the boundary layer over, or times delta T over the boundary layer. So, once we figure out how much energy is going into photosynthesis, we have the change in conduction and convection. It's how much energy does it have to give off, and once we know this, we can rearrange this equation to solve for delta T. So first, let's look at how much energy is going into photosynthesis, and this is 40, it's given in the question, 40 micromoles per meter squared per second. That's a pretty typical photosynthetic rate. Now the question says, with a specific leaf area of 25 meters squared per kilogram, you don't need to know that. That's information given that's not helpful in answering the question. It's just going to make the question harder. So think about what you need to know. This micromoles we multiply by the energy in mole of carbon. This is micromoles of carbon per meter squared per second. And there's 30 micrograms of CH2O per micromole of carbon. And then we have to still take that times 16.7 kilojoules per gram. This is of sucrose. And then we come out with, once we multiply this together, 20 watts per meter squared. That's the energy going into conduction and convection in here. So now we know this number. 2 sides of the leaf, K is a constant. Now we have to calculate boundary layer, and that we have all the parameters given to do that. In this particular case, boundary layer is 0.004 from the handout, that's a constant, that's given, times the leaf width and the wind speed, and those are given up above. Wind speed of 0.5 meters a second and a width of 20 centimeters. So this is width over wind. I'll write it in here. Wind, width, and this is 0.2 meters, and this is 0.5 meters per second, and it's the square root of that. This is just the same thing with the values substituted. Now we get a boundary there, do all this math, 0.00253. So, we've got all of our parameters here. This one goes here. This one goes up here, 20 watts per meter squared. Now let's rearrange this to solve for delta t. And once we do that, we have delta t is c squared over 2 times k times the boundary layer. And k is 0.026, constant from the handout. C is 20, boundary layer is 0.00253, 0.00. And now we just have 4 numbers, and we get those together, and this is, comes up, this is 0.0506 over 0.052, and the answer is 0.97. That's degree C for delta T. So this is how to work this out with set it up to work it out. That's a lot of heat, 0.97 degrees C when you think about it. But this would only happen with a really low wind speed. As soon as the wind started to blow a little, if the wind doubled, this would drop way down. But it's possible photosynthesis takes energy. And in this case, it would cool the leaf by pretty much 1 degree C to have for the photosynthetic energy. So when we say, oh, you can ignore photosynthesis, well, not always. There's times when photosynthesis is really high, and we can't, or we shouldn't ignore it. And this is one of those unique cases. All right, number 8 has 3 parts. And this is probably the hardest question on the test. And I remember when I was grading these, it was tricky because if you made an error in the first part, it carried through to the others, but I didn't take extra points off for that. Remember, this is 110 watts right here. Let's go through this one. Let's see. Does it help? Oh, can I put it here? Over here? So we got keep this right here. This is another boundary layer conductance kind of a question. And obviously you don't need all those component parts in the top part of this, but the narrow leaf is 0.49 C, the wide leaf is 4.86. Those are on the key. So this is, back back to conduction and convection, 2 times K times delta T times the boundary layer. And now we know that, again, we're going to solve, this is the same as this. We're going to solve right there for delta T, put the numbers in. I don't think I need to work this one again because it's so similar to what we did right there, only the leaf width varies a lot where we've got width in here. The key to this is getting the units correct for leaf width. And one of these is, get it read up here. 1 millimeter is the narrow one, 0.001 meters. That's like a pine needle, the narrow leaf. And I made these big so the answer would be big. And the other one is 10 centimeters, so that's 0.1 meters. So look, this is different by a factor of 100. These 2 leaves is a big difference. And in fact, there's pretty much, there's a 10-fold difference in leaf temperature when you substitute the values, a half degree. So this one, once you get this one set up, the calculations aren't difficult. Now we want to know the driving gradient for transpiration. And this, let's erase that. Now we're back to our stomate, like this, and the water coming out, and it's the driving gradient is delta H. So we've got H I inside the leaf, and then HA out here in the air, and the difference is the driving gradient in kilopascals. And note that the atmospheric pressure given above is 101.3 kilopascals. So after we get delta H, let me put the HA right here, HA. After we get delta H in kPa, this we did on the previous test. Now we need atmospheric pressure, barometric pressure, ATMOS pressure, and this number is given, sea level, exactly. This is dimensionless, because now we have kPa per kPa, that's what this asks for, dimensionless driving gradient. So obviously the big leaf, wide leaf, is hotter, so this driving gradient is going to be significantly bigger, even with the same HA in the air. Now we've got the final section of this, water use efficiency, that goes all the way back over there to that blue, or to that pink writing. And in either moles or grams. And remember, first we do moles, because this is all set up for moles. This, let me write this again, over here. Let me put it over here. Delta CO2 is already, let me put it up here again. WUE is delta CO2 over delta H2O times 0.625. This is already in units of micromoles per mole. This is in kilopascals, and once we divide it by kilopascal, it's kilopascals per kilopascal. Both of these units cancel, so that's two ratios, both of which are dimensionless units, but you gotta divide this one by kilopascals. Once we do that, well, you can see the answer there. You have to bring some of the values over from the previous one, but you can see let's see, the answers are given in the key. But this is exactly how to set it up. And I didn't leave a very big space here because these are all 10 to the minus fourth. These are all small numbers because the gradient for water coming out is huge and the gradient for CO2 going in is much smaller. And of course, delta CO2 is delta C is 30 grams of CH2O per mole of carbon, and H2O is of course 18 grams of H2O per mole of H2O. And the question just asks you to express it both ways. And it's trickier than it seems to think that through and what's the ratio. Both of these are tiny numbers and reflects how low water use efficiency is. But the water use efficiency of the narrow leaves is significantly better than the water use efficiency of the wide leaves. So, gee, if we want to breed plants for better water use efficiency, we ought to breed for really narrow leaves so the wind can cool them off quickly when they get water stressed. And it's something that breeders are working on. Okay, these are the hardest questions on the test. Let's go to the next one. And by the way, I pulled this in here. Here's the saturation water vapor pressure curve with the values here. You don't really need the curve, you just need the values. This is where you calculate the humidity gradients in the plant. All right, 9 shouldn't be too difficult. This is really similar to homework, and we just want to set this up correctly, and it's a quick calculation. When we rearrange this, put this in yet a different color, leaf area index is the natural log I sub O to I sub I over K. And after you've rearranged this, now it says for 95% absorption, so this is the natural log of, let's take 100 over 100 minus 95, because this would be 95% absorption. So this is the natural log of 100 over 5, or natural log of 20. And after you get to the natural log of 20 for 95% absorption, then we put the K values in to the equation. And the vertical leaf comes out to be a K of 10, and the horizontal leaf comes out to be a K of 3.3. So this is the key for that part, rearranging this equation to solve for the unknowns. 2 pages left. Number 10. This is sort of the, not sort of, this is the giant pumpkin question, rearranged. To work this question, you need to take, this is almost right where these things were when we did them in here, the 4 components of yield, and then look at typical numbers and look at high estimates of numbers. And this just asks you to do percent absorbed, radiation, photosynthetic efficiency, respiration efficiency, harvest index. This times this times this times this, get the answer. And then a typical input of photons at the top. Let's see. This is the current world record, by the way. This guy in Belgium, 2,624 pounds. It hasn't been broken yet. So 30 by 30 foot area, now you need to get that number in meters squared, because that's how much light's going to be available. Then this doesn't give a typical radiation input, so you have to assume that. Remember, a really bright day would be 60 moles per meter squared per day. Average might be 50 moles. This, when you calculate this, this is going to give you grams of dry mass per meter squared per day. But these pumpkins is only 8% dry mass. It's 92% water. So this 2,000, only 8% of that, 2,600 is dry weight. And the rest is just water, which doesn't, it adds to the fresh weight, but it doesn't add to the photosynthetic part. So, these are approximate numbers because it depends on your assumptions. But using realistic values, you should get a number somewhat over 1,000 kilograms for the whole summer that he had time to grow this. A typical 100-day growing season. This isn't this number is written to 3 significant figures, but somewhere between 1,000 and 1,500 is typical. But now you round this all up. You can do CO2 enrichment, a high quantum yield, 40 by 40 foot area, everything maximized. Now it's around 5,000 kilogram pumpkin. So that's just setting this up and putting typical numbers in here to get familiar with the yield modeling. The very last question is here, and I think what I'll do is put this right here, because we can work this out with a pencil instead of trying to put it on the board. This is a cold, clear night, and here's our parameters for radiation absorbed, radiation emitted, transpiration, conduction, and convection. They're not explicitly written on here, but they're given above. So 400's coming in, 500's going out, and there's no transpiration. So it's night, the stomates are closed, so there's only one possible number here that could solve this, and that is minus 100. And that means, minus means the leaf is colder than the air, and it's absorbing energy by conduction and convection to balance this. So that's the first answer. Now, we have also a cold, clear night, and the sprinklers have been turned on. In this case, we could have a radiation frost, but if it's still a cold, clear night, this is the same. It's still 400 watts. Now, it goes right to air temperature, and now we still have only one unknown right here. And that comes out to be minus 140, because the sprinklers are transferring the energy. Warm the leaf up just a little bit. So the energy that was cooling the leaf is now over here. It's absorbing the water, and the numbers balance. Now it's still a cold, clear night, so this one is still 400. Now the fans have been turned on, so the leaf warms up, and this number is going to get significantly bigger from warming. And if the leaf warms up slightly, this isn't an exact number, but we can figure 550 right there for emitted radiation because of slight leaf warming. And now there's only one unknown left, and that has to be minus 150 to balance the equation. And finally, same cold, clear night, but now these smudge spots have made a black cloud, and look, the radiation is warmer here because of the clouds coming in. Transpiration still 0. If the radiation has made the net radiation 500, the leaf could warm up to the air temperature. So that one could easily go to 0. It doesn't have to be exactly 0, but that would be a typical number. And now, this one right here is 500. It's actually, these are all plus 500s, to make the energy balance. So this is a matter of step-by-step thinking this through and getting the numbers so they balance. The exact numbers aren't important, it's just the concept, which direction do the numbers go. I wish you could be here to go through this in some detail, but this is at least step-by-step through how to work these. Go through all your notes and your homework. Go through your old homework assignments, but the ones that you've handed in and gotten back, even if you got full credit. I'll ask you questions that are related to those, only now you got to work them on the test. The test is open book, open notes, open internet, but there's one resource you can't use, and that's people. You have to work this on your own. You're on your honor not to. Now, some people have a dad who's a physicist, but oftentimes these questions are so specific that doesn't often help anyway. But you can't use people. Everything else is open. Starting Wednesday, I will email this to you at 1 o'clock, and you have 24 hours to work the exam. So, good luck. I hope you all do terrific. Thanks.